So guys, today we have Introduction to Probability, which is chapter 9. And probability is, we're talking about gambling, we're talking about playing games, we're talking about what's the likelihood of an outcome occurring. And probability, we always describe it between 0 and 1, okay? Probability is a number between 0 and 1, where a probability of 0 means it's not going to happen, okay? And a probability of 1 means that it's certain of happening, all right? And so then we have halfway in between, we're flipping a coin. Probability of getting heads, if it's a fair coin, 0.5. We have, 0.25, it's not very likely, 0.75, it's quite likely. And so probability occurs between 0 and 1, all right? So that's the first thing to say. The second thing to say is that the sum of all probable events is 1, Sam. So when we flip a coin, what are the possible outcomes that could occur? Well, you could get a heads, all right? You could get a tails, or maybe it'll land on its side, So technically, 3 outcomes. And if you add the probability of all of those events together, it will always be 1. The sum of all probable events is always 1. Okay. The more likely event, the closer it is to 1, and then we've got conditional probability and replacement, which we'll talk about here. Okay, so we've got a standard deck of cards. This is our first question. A standard deck of cards. So that means it has ace through to 5, 6, 7, 8, 9, 10, jack, queen, king. Okay, standard deck of cards. And we've got 4 suits. So we've got it in clubs, spades, diamonds, and hearts. All right, so we've got 13 cards and 4 suits. 13 times 4, 52. There's 52 cards in a standard deck, right? 4 aces, 4 twos, 4 threes, 4 fours. Okay, given a standard deck of cards, list the sample space if the events are A, suit, B, value, and C, colour. All right, so this is our answer for B, all right? The value, the possible values that you can get if you're randomly selecting a card from a deck of cards. You could get an ace, you could get a 2. This is the sample space. This is the list of all possible events that could occur if you're randomly selecting a card from the deck of cards. All right, for part A, the sample space for suits. If you're randomly selecting a card, what are the possible suits you could get? Well, you could get a heart, you could get a spade, you could get a diamond, and you could get a club. So that's the sample space. Okay, and then for the last one, if you're randomly selecting a card and the sample space is colour, what colours it's going to be? Well, you either get a red card or you get a black card. Okay? Alright, so sample space is just a list of the possible events that can occur. Now let's move on to question 2. All right, now what we're evaluating here is what we call theoretical probability. Theoretical, and that's contrasted with experimental. All right, so theoretical probability is what we evaluate in maths when we assume that the deck is fair, that it's been shuffled, we assume that a coin is fair, that a dice is fair, etc. Experimental probability is what the values you obtain when you perform a probability experiment, rolling a dice 100 times, flipping a coin 1,000 times, whatever it is. All right, and obviously the more times you perform an experiment, if the experiment is fair, you expect it to match the theoretical probability. Okay, so let's have a go here. So given a standard deck of cards, what is the probability of randomly selecting one card and it's a king? All right, so in a deck of cards, there's 2 ways to think about this. In a deck of cards, there are 4 kings out of 52 cards. So if you're randomly selecting one, the probability of getting a king is 4 out of 52. Now this will simplify to 1 out of 13. All right, and you can see here, if this is all the possible events, one of them is a king out of 13 for each suit, right? So 1 out of 13 is the probability. Okay, part B. How about a red card? Well, in a standard deck of cards, half of them are red, half of them are black. So we would have 26 out of 52, or half. All right, how about a diamond? Well, there's 13 hearts, 13 spades, 13 diamonds, and 13 clubs. So we expect 13 out of 52 to be diamonds, which is a quarter. All right, now we're accepting either of these. All right, you can write these ones, you can write these ones. It's just a statement, right? Okay, how about a face card? A face card is a card with a face on it. So that's going to be these ones here. All right, we have one jack, one queen, and one king for each suit that has a face on it. So we can see that's going to be 3 out of 13. 3 out of 13 or 12 out of 52. 12 out of 52 because there's 3 jacks. 9 out of 52. What have we done there? 9 out of 52. 3 jacks, 3 queens, 3 kings. 3 out of 13. 4 jacks, 4 queens, 4 kings, yeah. 12 out of 52. 4 jacks plus 4 queens plus 4 kings, in total 12 out of 52 face cards, or 3 out of from each suit. Okay, an 8 or a 9. An 8 or a 9. So here we're talking about these ones. We've got 2 out of 13. Okay, so for part E, 2 out of 13. Or you can say there's 4 8s, one from each suit, and 4 9s. So that would be 8 out of 52. All right. So you can answer like this, or you can answer like this. It doesn't really matter. Make a connection. Okay, this one's going to be a bit trickier. A red card or a king. So we might be inclined to think, all right, there are 26 out of 52 red cards. Okay, and then there are 4 kings. But the problem with this is 2 of the kings are red already, aren't they? So that means 2 of the kings are included here, which means only 2 black kings we can add to it. So we have the red cards plus the probability of getting 2, one of the black kings. We've got 28 out of 52. Now here it was useful for me to express both of them over 52 straight away, because then you can just add them together. If they have the same denominator, you're just adding the numerators, right? 28 on 52. And that can be simplified. Okay, how do we simplify fractions? One answer is to put it in your calculator. Another answer is to keep dividing it by 2 until you can't anymore. What's the highest common factor? 7. So like here, we can divide both of them by 4. By 4, so that goes to 7. Let's divide by 2 and then by 2 again. So we'll have 14 on 26 and then 7 on 13. Very good. So that's for F. And now for G. What about a king? So here we're introducing you to conditional probability. So we're performing the experiment twice. All right, so we're not just randomly selecting one card. We're randomly selecting a card, and then we've got a king followed by another king, either with replacement or without replacement. So let's decide what they mean. So, firstly, the probability of getting a king, randomly pulling out a king. Okay, we'll do part I first with replacement. The probability of randomly pulling out a king is 4 out of 52. All right? But then, we are going to pull out one more king. All right? And it says with replacement. So that means we've pulled the king out and we've put it back into the deck, shuffled it, and we're repeating the experiment again. So the probability of getting a king the first time is 4 on 52, and the probability of getting a king the second time, given the deck stays the same, there's still 52 cards in it because we put the king back in. Okay, so we have 4 on 52 multiplied by 4 on 52. That these events are what we call conditional on one another. All right, so the probability of getting the first king multiplied by the probability of getting the second king. Another way you can think of it, what's the probability of flipping a coin and getting 2 heads in a row? Well, getting a head the first time, 0.5. Getting a head the second time, 0.5. 0.5 times 0.5. Okay, so that's how you can think about conditional probability. You have to multiply them together. So that's, anyway, that's going to be 3 on 13 times 3 on 13. We've got 9 on 169. It probably will simplify. We'll put it in our calculators in a sec. Okay, but let's move on to the next one. Because the next one says we're drawing a king and then drawing another king, but this time without replacement. Okay, so the probability of getting the first king is 4 out of 52. And the probability of getting the second king. Now, if we've pulled one king out, that means there's only 3 kings left out of 51 possible cards. So this is what we'll be performing for the second. All right, so the first one with replacement, the probability remains the same. The second one without replacement, the probability changes because we've removed one of the cards from the deck. It's no longer a standard deck. One of them's been pulled out. So if anyone's got it for me, or point it out. Just do it in my head really quickly. 52 times 51. 2652. The simplest way to write it, so what it's going to be is 12 on top of 2,652, and that simplifies to 1 on 221. Okay, so I'm expressing these as fractions. If you put them in your calculator, you can convert them to decimals as well. Remember I said a probability is always a number between 0 and 1. All right, so you can convert this to a decimal by pressing the Serve to Decimal button, and you get 4.5 times 10 to the minus 3. Okay, so 0.0045. So just pointing out, we'll accept either fractions or decimals. Fractions are useful for when you have to add probabilities together. Very good. We've got one more question to get through here. What's the probability of getting 3 number cards in a row? All right, the first one says with replacement. The second one says without replacement. So we'll just clear a little bit of space here. Okay, so 3 number cards in a row. So we'll consider an ace as a number card. All right. So what we can see is there are 10 number cards for each suit. So there are 40 number cards out of 52. Okay, so the first one says with replacement. So if it's with replacement, that means we're randomly selecting a card and we're saying what's the probability of getting an ace, 2, 3, 4, 5, 6, 7, 8, 9, or 10? It's 40 out of 52. Okay. We got one, we put it back in, and now we're going to shuffle it and randomly select one again. The probability remains the same. Okay? 40 on 52 times 40 on 52 times 40 on 52. Probability remains the same because it's the same deck. We're putting the cards back after we've performed the experiment, and the probability of getting a number card is 40 on 52. Okay? So let's evaluate that. 40 on 52 to the power of 3. 0.455 or 1,000 on 2,197. .455. All right. So again, whenever we want to clear a bit of space to make the point. Whenever we write as a decimal, all right. The reason we express as fractions is because it includes every decimal place. All right. So it's sort of a bit more precise. If you do write it as a decimal, 4 figures, and then round the last one, so we've got 3 significant figures. Okay, so that was with replacement. Now we've got 3 number cards without replacement. So that was H part I. So now it's part 2. So we've got a random deck of cards. The probability of selecting one card and it being a number card. Well, a number card, we've got 10 out of 13, or 40 out of 52. So we have 40 out of 52 multiplied by, okay, the probability, we've pulled one number card out. We're not putting it back this time, which means we've only got 39 number cards out of 51. All right, and then we've pulled 2 of them out, which means there's only 38 remaining out of 50. So this is what we're performing to determine the probability of getting 3 number cards in a row without replacement. So we've got 40 times 39 on 51 times 38 on 50. 38 on top of 85. All right, again, I'll convert it to a decimal for us. 0.4470. 0.447. Okay, any questions? So I'll see how we go today. It'd be nice if we can move on to tree diagrams because they do flow on quite nicely. But let's have a look at our checklist. What questions have I written down? So we're chapter 9. Okay, there's a few questions from 9B, 9C1. So you can do today 9B, 9C and 9D. I reckon that might be enough if we do them. There's quite a few questions there.